Explaining um I guess physics applications to calculus. Everybody knows calculus was pioneering the early physics. So let's start with the definition of work. Work is essentially the force times distance. That's just the definition for the first part. But that means that if you take a graph of force, assume that this is a constant force and this is a distance such that F times D equals W, we can see that W is just the area under the force versus distance curve. Thus, we can write W as the integral of force with respect to distance as the x-axis. And I guess I could put ds here because x would be a little bit confusing to write. So yeah, that's literally all that is. So if you're given the fact that force is equal to x plus 2x, where x equals distance or displacement, then you can just rewrite it as the integral of whatever to whatever of the work. And in physics, you learn that work is a change in kinetic energy, which tends to be the case when, or which is always the case, of course, but you learn that work is equal to the change in kinetic energy, which is pretty fascinating as well. Though I don't think that is necessarily required for physics. This is simply just a summation of work. Obviously, work is also MAS, and MAS equals MAS is equal to VF squared minus VO squared divided by 2, and then you can plug that back in to get the change in kinetic energy formula, but physics doesn't work about this. So now we get to Hooke's law, which has to deal with springs, but I guess that's irrelevant. All that matters is this is the formula for calculating force. So that means if F equals kx, and we're told that a force of 40 newtons makes spring stretch 10 to 15 meters, then yeah. So we can also, since this is linear, we can also rewrite the delta F as kxo minus xf, which is going to be the same, or xf minus xo, same thing, which is going to be k15 minus 10, which is 5k is equal to the change in force. We said that there was an applied force of 40, so k is equal to 8. So that would be the spring constant. And now, since we know what the function of force is, we can now integrate it with respect to displacement once more. And now we can calculate the formulas for the things. Obviously, you can also do so with abstract things. So if you do like, well, since before we just figured out that the formula is 5x. Was it 5x? Yeah. Oh, actually, I did it in respect to centimeters, which is a little bit not right. So we have to do it for e equals k5 centimeters, but to convert this, it's divided by 100, so it would be k5 times 10 to the negative 2, which is 5 over 100. And dividing it, k equals 0.08, or no, sorry, 800. So that means you have the formula f equals 800x. Now you can just integrate it with respect to displacement, of course. And we're told that it gets displaced from 15 to 10, or 0.15, or how much work is required to change it from 10 centimeters to 15 centimeters. Now we know what the force is at all times. We can just simply plug this back in, or 15 to 18 centimeters. And 18 centimeters is 0.81 meters, and 15 centimeters is 0.15 meters. So integrating it, we get 400x squared. And you can now plug that in the lower end upper bounds to get your function, or your value of the work that is made, which is just force times distance, or the integral of force with respect to distance. Of course, you can also do this with arbitrary Hooke's law, which makes it so if you integrate with respect to x, or actually b minus a, same exact thing, or actually you could do xf and xo of kx, you get kx squared over 2, which is exactly the potential energy formula. Actually, this would probably be the more accurate version. And since kx is the force with respect to distance, then the change in work would be kxf squared minus 2 over 2 minus kxo squared divided by 2, which is exactly the change in work done to the spring. And remember that the work is the negative change in potential energy, so then you could get kxo squared over 2 minus kxf squared over 2, which is the work you do on the block. which changes the kinetic energy of the block, or just the mechanical energy of the block. Depends on if the spring is part of the system. But that's just all physics application. So I guess that doesn't matter. Now we get to Riemann sums with trapezoids, which is quite easy too. So actually, I could probably prove this, but I haven't tried before. So let's start with the trapezoid formula. Okay, let's take an arbitrary value of a trapezoid, which is going to look something like this, from what I remember. It's been a while since I've taken geometry. So we have to label the heights B1 and B2, I believe. B1 is this side and B2 is this side. So on a curve, yeah, this is just the formula for a trapezoid. What am I talking about? Let's say that this is base H, which would technically be equal to delta X. The formula of a trapezoid would then be delta X times B1 plus delta X times B2 over 2. Is that the formula for a trapezoid? Well, I know they take the midpoint. Let me think. So you could factor out a delta X, B1 plus B2 over 2. Alright, and let me search the trapezoid formula. So the trapezoid formula is H times A plus B over 2. That's interesting. A plus B. Oh wait, that's what it is. Trapezoid is this, right? Then wouldn't it just be? Okay, there we go. That's why. So apparently this is not a trapezoid. This is just the rectangle with the triangle on top, which is actually used in physics when you have a constant variable acceleration. So here the formula should be delta X times B1, which should give you this entire shaded region, plus delta X times B2, which should then be equal to delta X times B1 plus B2. But where does the divided by 2 come from? Don't know. Okay, well, anyways, I guess that's irrelevant. I will have to find the proof later on, though, but I don't know why it's not working. Okay, anyways, so Riemann approximation using trapezoids. Take a curve and draw the curve. Before we use rectangles, now we will use trapezoids. The formula is T equals delta X over 2 times XO plus 2X1 plus 2X2. And so on and so forth. What is it? It's 2f of x2, 2f of x1, and plus 2f of x3, all the way up till 2f of x up n, which is the formula. So now you can use this for other things and calculate the function. So let's do a question. So this is just integrals again. There's 4 types of Riemann sums: midpoint, left, and right, and a trapezoidal approximation, which is what we're doing here. So now we just get to Simpson's rule, which is also pretty easy, but it's just another formula. I still haven't figured out the proof because I just read it 5 minutes ago, but it has an alternating for y1, and I don't know why they use y here, actually. I don't know why they don't use f of x of 2 or whatnot, but I don't know why my book uses this, I guess, but and the last number should just be that y height. The proof, I'm not too sure, but I think it has something to do with the last and the first averaging out, and it has something to do with curve fitting with approximate polynomials, which has to do with Lagrange multipliers, but still I haven't figured out the full entire proof. So this is the Simpson's rule for calculating any approximating formula, or any approximating area of a curve or under a curve.